Okay, hi. My name is Noam Neeman. I am Fed at Wix Answers from Tel Aviv offices. The handsome guy right here is Oded Soffrin. He as well is a Fed at Wix Photographers from Israel. And I must say, first of all, thank you for having us in Vilnius. I'm a professional runner, by the way, and I ran on the river and through the city, and it's a beautiful city, and I really enjoyed it. So you have an amazing city to live in. Right, so we're here to talk about WebAssembly. WebAssembly, which is WASM for short, an efficient, low-level bytecode for the web. So this is our agenda for today. It doesn't make a lot of sense to talk about WebAssembly without first realizing the cost of JavaScript that it was before, and basically just the history of how JavaScript engines work. And we'll continue on for the initial steps that came to be, that brought WebAssembly into power. And we'll continue with talking about what is WebAssembly, what it's good for. We'll follow up by some cool demos. And then at last we'll look at the future and what's our role in basically with WebAssembly as front-end developers. So the cost of JavaScript, have this thing. There is a really good article by Adi Osmani, he's an engineer manager at Google working on Chrome team. This is the article. It's called The Cost of JavaScript, and a lot of the next slides are excerpts from that talk, and I really recommend that later or some spare time you go and read the whole thing. So we'll start at the very basics of how a web app works. So the browser, here it's just depicted on an iPhone, but it doesn't matter. The first initial request to the server comes out, and the server responds with an HTML, hopefully. And the HTML basically tells the browser which resources it needs to download. It could be the CSS, the JavaScript, images, whatnot, whatever it needs to load. And the server responds. As developers, we usually think about these lines, about like how big they are, what's the size bundle, and we do a lot of things in order to bring that size down, to make JavaScript work fast for us. In a way, we're trying to bring as least code as we can, so the browser is not so the network requests are not very huge, and eventually we're hoping that things will run faster. But in reality, there are a few steps that actually happen that we don't take in mind in enough seriousness. So the first, decompress, that's just for gzips, but the next step is parse and compile. And parse and compile are steps that we don't necessarily think of. So what do we do to minimize packages that are sent? We do all these really, really nifty things. There's amazing things that happened to us in the last couple of years. We minify and we do code splits so we have dynamic imports. We do tree shaking so we don't send unnecessary code for our web apps. We optimize vendor, we transpile code, we do hosting, and all these things just so we don't send a lot of unnecessary code. And like I said, what's mostly forgotten is parsing and compile time. Have anybody seen this screen before? So this screen is called bottom up. It's one tab out of the whole performance tab under Chrome DevTools, and specifically this bottom-up tab can show you a really interesting thing about JavaScript. You can get the whole time that JavaScript used out of the total load time, but you can also see what the breakdown of the compile and parse out of that whole time measurement. And as we can see, in a 3.5 second measurement, 21% of it was compiling and 8% was parsing. This adds up to 2.2 milliseconds. This is quite a lot. It's something that if we can bring down, it's something that the users will definitely feel. What's parsing? We're talking about parsing here. So parsing is that stage where the engine takes, this might be obvious to some of you, the engine takes the JavaScript code that you send it and it parses it to an abstract syntax tree. And then the compiler, the engine, basically takes that abstract syntax tree and runs it. This is basically how it looks like roughly. So there's the compile at first. We do the parsing. We do the compile and optimize. Some of the optimized code gets tossed away. Then we do re-optimization, and we end up executing some code that we optimize, some that's not optimized, and somewhere in between. And at the end, we do garbage collection. That's basically what happens to a resource that has been downloaded. So next up, this is just to show the cost of parsing. So this is just a comparison between a CNN site. It's the package that CNN site sends to the browser. And as you can see, on an iPhone 8, for example, this can take up to 4 seconds. This is the parsing. It can take up to 4 seconds for just the scripts to get parsed. On a slower phone and a more average phone, like a Motorola G4, this can be up to 13 seconds. And that's a crazy amount, and that's only for parsing. OK, so now that we talked about parsing, we know that the cost of parsing JavaScript is high. We can go to the next step that we talked about earlier, that we mentioned, and that's compilers. And what we're going to talk about actually is just-in-time compilers. And there's an article by Lynn Clark of Mozilla called A Crash Course in Just-in-Time Compiler. And like before, I really urge you and recommend that you go and read her blog and her blog posts. She has some really nifty cartoons in her articles, and some of them are in the next slides. So credit goes to her. So I was talking about, I'm talking about just-in-time compilers. And but first we need to understand, why are we talking about compilers? JavaScript usually runs as an interpreted language. That's what probably most of you know. So we will get to that. But first, let's outline the possibilities. So an interpreter, which is here on the left, it takes one byline, it reads one byline. Now, it doesn't do this, it takes it from the abstract syntax tree, but for the sake of illustration, we'll show it on those lines. So it reads line by line and turns those lines into machine code that can be run on the processor. This process is very fast to start with. So let's say when you have the code, you only need to compile that one line in order to run it, and then you can move on to the next line. On the other hand, on the other side, we have the compiler, and obviously these are rough examples. And the compiler takes that whole code, does a few assumptions to it, does optimization, takes its time into compiling it to machine code, code that can be run on some specific processor or architecture. And it can do a lot of optimizations on the way. It's taking time. I'm guessing that if any of you who ever compiled code before, meaning not using JavaScript but using some C++, C, or some other Swift or some other code that gets compiled, you're waiting. You wait when you compile. You wait and you wait and you wait, and that's something that is not really appropriate for web development. So when we pass the code to the user, to the browser, we want it to run very fast. That is why, long time ago, when JavaScript just came to browsers, the browser vendors chose to use an interpreter. And that's how, that is really how the browsers ran up until 2008. Up until 2008, they ran exactly like that, one line by line, and every time the loop came back again, every iteration of the loop, the line was interpreted again and ran again. As of 2008, and fueled by the browser wars, the browser companies looked for various ways to make their browsers faster and faster. They're trying to take more users. And the way to make them faster, one of the ways, meant to run the site that users visit, run it faster. That means trying to make the code run faster or in the browser. Then came in the just-in-time compilers. Basically, all of the browser engines, they do it similar, not exactly the same, but the concept of just-in-time compiler lies beneath every one of those engines. So just-in-time compilers was not new in 2008. It's originated in 1970s over Lisp language. Just a fun fact, but they only in 2008 they only started incorporating this. So what is a just-in-time compiler? It's basically an interpreter, but you add another component to it. The component is called a profiler. This is this dude with the sign. That's a profiler or a monitor, in other words. And when the code is interpreted, so when it's interpreted in the first run, it just runs like every other engine before it. Just interprets line by line. But the profiler and monitor's job is just to count the frequency of which the exact line is run. So if this line, for example, this line would happen once, so it's not very frequent. But the lines inside the loop, the iterations, are going to be ran more and more times. So the profiler takes note of all these lines that run more and more times. So basically, it takes that whole function just for this illustration, and it's saying, okay, this code is running frequent. So when the same line is run again and again, the monitor marks it as a warm, and then it has it sent to a baseline compiler. This is another dude here. It says go to a baseline compiler, and then the compiled version is saved as a stub, and then it's saved on the side, and then a stub is put in place of that function. So whenever we go to run that line again, or that part of the code again, we just pull the compiled version and run that compiled version. That compiled version is going to be faster than just reinterpreting again and again. If it's not always worth it, it's worth it only if the line is hot, right, or warm. Then only then it's worth it to compile it. But we are in JavaScript, and to compile some code that we don't know exactly what it is can have the very different meanings. For example, this line is do you see it back there? It's sum plus equals array of I. This could mean a lot of different things. It depends on the type that sum is. It depends on the type that array is. Maybe array is not an array, and it depends on the type that the value of the array is. And these two different, if in different branches here, it can lead to very different processor instructions, because adding strings together or concatenating them is not the same instruction as adding numbers or floats one to another. It's a very different processor instruction. So the baseline compiler takes note of all of that and makes versions, different compiler versions, to each and every of these options. There are some other optimizations that the browser does, but it basically does compile for all of the options that come by. And it has all these assertions because every time that it comes up to a step and tries to pull compiled code, it needs to check which version it's taking. So it makes all these assertions on every step of the way, and that could be expensive. So at runtime, like I said, it's going to ask itself: is sum an array? Is sum an int? Is array an array? Is I an int? And all of that. And it has to choose the correct path. And all these assertions are very expensive. One optimization that it can do, for example, is just test some of them beforehand and not test all of them. Only the ones that are able to change. Maybe that's an optimization that can be done. And move the assertions outside of the loop. And that's exactly what the optimizing compiler does. So the optimizing compiler kicks in only when a line becomes running more and more and more times, and that's when it's boiling. It's like a really hot line. So it's really worth doing all the optimizations, and it does that by it makes a faster compiling code only because it's taking assumptions over the code. For example, it makes use of, for example, if it takes an array as if all the values in the array are numbers. For example, that's like one example. And then it runs, when it reaches the code again, it runs that line only if the assumptions are true. And then it will have to still check and make sure the assumptions that it's making are true. There is one caveat that if the assumptions turn out to be false, then we bail out. We throw that very optimized version, we throw it out, and we continue with the baseline compilation. And if we go through all these again and again, if we try to optimize and then we bail out, and we try to optimize again and then we bail out, then we can end up with code that's actually a little slower than just running the code or just using the baseline compiler version. And that can be frustrating because people want code to run fast. But the upside is that just-in-time compilers turn out to be 10 times faster on most average code that is not really abused towards the optimizing compiler. Then it's 10 times faster than just the interpreter, and that's a huge case for using them. And all of the major browsers use them. Okay, so history of WebAssembly. ASM.js. Have anybody heard of that? Not a lot. It's like maybe 10 people here. It's a proprietary technology. It's developed by Mozilla, and it first appeared in 2013, so only 5 years ago. What it is, it's a subset of JavaScript, and it's, I'm quoting, designed to allow computer software written in languages such as C to be run as web applications while maintaining performance characteristics considerably better than standard JavaScript. The main idea is to use a version of JavaScript that is just stricter than JavaScript itself, and I'm not talking about strict mode, just a lot stricter than JavaScript, and that will help and will make the job of the optimizing compiler. It will make it easier, and we'll have less bailouts, and we won't need to do re-optimization of code. And one example of that is the elimination of dynamic types that we have in JavaScript. So we don't have to eliminate them, but because it's a subset of JavaScript, it's only we will see it in a few moments. So this is regular JavaScript. This is how everyone here writes code. Maybe not with the var anymore, but this is just like regular JavaScript. It's an assignment. Second gets assigned to first. First equals 5. And this is how the ASM version is going to look like. This comment is blurred, but I will explain it. Basically, we're just assigning 5 to first, And by using this bitwise operator here, the bitwise OR to 0, we make sure that the variable second is always treated as a 32-bit integer. And this way we can make a lot of, not we, but the optimizing compiler can make a lot of good assumptions over the code and run it a lot faster. And this is apparent in computative expensive tasks. So ASM.js follows rules like that, and by combining these rules with the normal JavaScript, we can gain much faster code, even faster than after just the JIT engine introduced. And it will help. It just helps skipping a lot of optimization steps. But no one wants to write this code, right? But no one can think about this code, and no one writes this, and it's very, very hard to maintain code like that. So, and that it was actually not the thought behind ASM.js. So what ASM.js is, it's basically the output is ASM.js, but the input is C or C++ or some other language, usually statically typed. And it passes through this stream of compilations. So these are compilers, and script 10, like you say, it's a Mozilla project, and basically we'll just like write C and C++ code, and the result will be in ASM.js. And these tools are free and easy to use. And highly maintained. So what do we get by using ASM.js rather than regular JavaScript? We get faster code. This is just a chart over calculating the Fibonacci sequence. And as you can see, ASM.js code did 25% faster than regular JavaScript code, which is amazing. 25% is enormous improvement. And it's
regular JavaScript is JIT compiled, right?
Sorry?
The regular JavaScript is the modern JIT compiled code.
Yes, that's the modern JIT compiled code, and this is ASM.js running inside the modern code, the modern engine, the JIT engine. And this is just a native code comparison. So you can see there is still a way to go. And just to show you, oh, just 1 second. So I said it was ASM.js was introduced in 2013, and in that year there was a port for Unreal Engine 3, which is a gaming engine, that was beforehand not on the web, and it was ported to the web over ASM.js in 4 days. It took them 4 days to do so, and it's so straightforward to port these that someone actually did this. And I'll show you. So this is just a regular web browser, and there's Windows operating in it. So they just ported Windows 95. I'll go ahead and I'll open Solitaire. And it's just actually Windows 95. So I think that's beautiful. And that's only one part of what you could do. So finally, after going through the history of how JavaScript runs in our browser and the uprising of ASM.js, we're trying to get code run even faster. And we want to move on to the next iteration of this. And I'd like to invite Oded Soffrin, again from Wix Photographers, to tell us more about it. It will take us.
Okay, finally, WebAssembly. So JavaScript was born in 1995, and we got through all the history until 2015. In 2015, a group of people said, enough. It's technology from 2 decades ago. We had profiler and compilers and JIT, and we tried to optimize and make the most of it, but it was, as Noam displayed, it was meant to act as fast and to do some static changes in the static page, dynamic changes, sorry, in the static pages, and there's a whole ecosystem which was built on top of it. So they sat down, they made a community group, and they sat and thought. It's the same people who brought us Internet Explorer and Chrome and Firefox and Safari and representative from LG and Facebook and every big company that holds stakes in the web as we see today. And they decided we need something new. So in 2017, an MVP was launched, supported by all modern browsers, which is WebAssembly. What is WebAssembly? Essentially, it's a portable compiled target, which means it's not compiled to a specific machine type. It's compiled to a virtual stack-based machine. It's here I'm demonstrating a text representation. WebAssembly is compiled to binary, but since we want to see it, it's compiled to something like this, which is a set of instructions for a stack-based machine, which is used also in for performance. It's designed for that. So here we see a function which receives a parameter p, and which is integer, 32-bit. And what this function does, it takes this param and put it on top of its stack. That's the first line. And then in the second line, it takes this param and put it on top of its stack. And then the third command is to combine them, the first two integer on top of the stack, and return the value. So essentially, multiply by 2. As ASM.js, nobody wants to write like that. So let's see what does it mean, portable compile target. So if we think about compile traditionally, what we know as compiled, it means we take the low-level source code, C, C++, Rust, for example, and through intermediate representation, we get binaries for specific system, for Windows, for Mac, for Android, for iPhone, for Ubuntu, you name it. In WebAssembly, we do almost the same, but not the same. We don't go as far as the specific architecture of the machine, but we stop in the virtual instruction, which all the browser can support, and do the final hop to compile it to their own architecture. So we do as much as we can in compile time, and we can do in this compilation time, which done beforehand, all the optimization, and we left with the most efficient, because it's stack-based instructions, minimal code base we need to serve to the browser and let him do the last step so it could run. So as opposed to interpreter, it's something completely different, a new paradigm. A valid question may be, why is that so good as opposed to what we have? Because it needs to be really good to replace JavaScript. JavaScript is old, that's true, but it's experienced. Like we have so many developers and so much tools and tool chains and ecosystem. It will be, have to be like a revolution to change it. So there are 3 main reasons. All of them are good reasons, and we'll go over them. It's speed, portability, and flexibility. Let's check out speed first. So this is a reminder of how we do it on JavaScript. We get the packets, sorry, Opa. We get the packets coming in. In the most optimal situation, we can parse them on a different thread, not on the main thread. But after parsing, we have a single thread to do everything Noam talked about. The compilation, the optimization, the bailing out, the recompilation, the garbage collection, and everything interrupts up in the middle of the execution time. We start as fast as we can, but we pay performance price as we go. This is WebAssembly. And what I show here is how Mozilla deal with it. Mozilla is kind of the leading in the WebAssembly competition, although everybody playing along pretty nicely. But they are the first to implement all the proposals and make it the fastest as it can be. So here we see the packets coming in the same. We have to download the code, right? But during downloading time, we do streamline compilation, meaning the packet come in and we can compile the packet and carry on. And we can do it on multi-thread. So by the time we finish downloading all the code, it's compiled and ready to go. So we're starting off from, in comparison to JavaScript, to the baseline compiler, which is called in JavaScript during execution time if the line gets called a lot. Here, all the code is already baseline compiled, and we can start running from that point. But we can do even better because we can use, again, multi-thread to do the optimization, which is the next level of the JIT, like for the super boiled hot code. So we started running on the main thread, but we use different threads, which not interrupting our performance to do the optimization needed, and we can hot swap it and carry on without the user even noticing something happened, just that it works amazingly fast. Portability. These have two sides. One side, which is like ASM, there's no change there. We can take libraries from C, C++, Rust, Golang recently, and more languages are able to be compiled into the web, and just deploy them to the web as Lightroom have an online version. It's WebAssembly and Unity and Unreal Engine, and we see more and more big apps having online presence. But on the other end, we take our code and we compile it once, and we know it will run everywhere. We don't have to worry for different binaries, for different systems. Every device that can run a modern browser will have no problem running our code. It's minimum support. And the last reason, flexibility. We, as developers, we need as much tools as we can to solve a problem. WebAssembly is a great candidate for a CPU-intensive task. Video editing, image manipulation, gaming, everything that is hard for the CPU and deals with computation might be a very good solution to move it to WebAssembly. It doesn't mean JavaScript is gonna disappear. JavaScript does some things really good and which will be hard to replace with C code. But we can choose our tool for the right job. We can decide whether we use a module of WebAssembly or framework with JavaScript, or depend on the problem we're facing. Okay, now to a fun part. Wish me luck. Okay, what I want to do. Okay. What I want to do is to show you an example of usage on WebAssembly, like how we do it, how we can do it today. So I made a kind of a CD application. Can you see it? It's big enough? I have a, let's start from C. I'm a front-end developer. C is not my strong side, but I managed to write this code. It's similar to the code we see in the virtual stack. It's a function that takes an int and return the duplicate value of it. So first step, we have C code. We want to make a WebAssembly model. So I have IMSI script and compiler loaded on my in my terminal, and you can. There's all kind of parameters here. I'm not going to get into each and every parameter, otherwise we won't get to the next talk. But basically, I'm telling him to compile only my code, none of the C libraries, And I tell him what function I want to export, which is multi. You can see that's the name I gave to my function, this one. So this is the module I want to use. So I compile. It's very quick because there's not much code there.
Why name is built on the underscore?
This is the annotation of it's your name combined with an underscore before. I guess there's like some namespace, and they want the user function to be marked somehow. So I compiled. We can see the module is created. And let me just save the app so we can see it in the browser, but I want to go over the code first. So the WebAssembly we saw, the binaries I'm not going to open. And I have an HTML. With the module, we're going to see it in a second, WebAssembly loader. It's a few lines I wrote. I gave to the, which exports init WebAssembly model to the window. I use it with my file. I get my exports. I console log my exports. And I have another amazing piece of code here. Button, state of the art. That on click, it console log the export of multi times 4. Let's check out really quickly the WASM loader to see there's not much magic there. Okay, so here we're using a few. We said the WebAssembly is supported by the browser, so there are a few objects introduced here. One of them is the WebAssembly memory. When we use WebAssembly, we have to define how the memory is being handled. There's a lot of parameters here, which mostly obligatory. Part of the work of WebAssembly, the post-MVP work, is to make this area more straightforward. But I define initial memory and maximum memory. My application doesn't need much memory, and what form the memory takes, and the memory based, and the stack max, because we said it's a stack machine. And essentially, we should go over it, but it's the imported object, the config for the WebAssembly. And then this is the function I import to the window. Init WebAssembly, it's get the path. It's used fetch to get the file itself, the string representation. I treat it as an array buffer to get the actual bytes. And I use WebAssembly supported method to instantiate the bytes into a WebAssembly module. I return the instance export, which is the instance created by my code. And we can see the result. Okay, so here's my title. Here's my button. And we can check the console log. First off, we see this works. On load, it was initiated, and we got the exports. I can check it out, the object. I see I got multi, it's a function. I'm pleased. I click on the button. I got a response. Amazing, it was fast. I told you it was fast. So we send the message to the WebAssembly world. It did the computation over there and got back the response. I can change this. This is gonna look pretty silly change. I can change it into 2. I will change the button as well. And I reload. And it still works, obviously. But the point here, I didn't have to recompile. My module was built, and it's done. I can serve it, I can use it, somebody else can use my amazing module if you want to double up numbers.
What will happen if you pass turn?
Good question. I expect it will blow up in flames, but like this.
Yeah.
You can't really pass string to WebAssembly yet. It silently failed. But we'll get into the what we can pass and what we can get back in a second. So other can use my model, and I can use other people's model. I can use, once somebody makes some logic and packed it up into WebAssembly module, I can fetch it and use it, and it's just another, like NPM package, just different, for different tasks. Let's see some example not written by myself. Less good examples, but also valid. Okay. This is a skeletal animation powered by WebGL, which is a graphic engine. The point in this demo, the same logic was written twice. Once in JavaScript for WebAssembly, for WebGL, and once in WebAssembly. There's a small screen here on top, you can see it maybe, of how many runners I can have. I can change it, the start in the background and running. We see if I have 100, it's kind of slowish in JavaScript, but I can switch to WebAssembly. Oh, nicer. Another example. Another example. I'll refresh that example. Switch to webcam. Switch to video. Okay. Video editor. Here might be a good place to say WebAssembly can't do everything automatic better. Even if we look in an example of a WebAssembly, of a video editor, which is like supposed to be classic for WebAssembly, CPU intensive, we have CSS filters. We have other support for stuff. There's some filters here. If we have like Sepia, we can just do the CSS filter. It will be much more efficient than have any computation layer by other module. But I'll choose one which is a bit harder, which is finding the edge and displaying them. And we can see WebAssembly is doing better. Not always, and not by much. It's definitely an improvement. Sometimes you get to 50% in this case. But point of it, I'm going to open it in Firefox also. And as we said, Mozilla is leading the way. I'm just waiting for a second, so it will. Here we go, and you can see how fast the WebAssembly in Firefox as opposed to Chrome.
So maybe they're JavaScript engine.
That's also true. But even if you look in you can see the JavaScript. Sorry, I don't see. Computation time is higher than the JavaScript computation time in Chrome. But you can see the WebAssembly computation time is smaller. It's like about 50% smaller.
We're losing the FPS on Firefox. Well, we don't.
Yeah, because they display it twice. They display it in JavaScript and display it in WebAssembly. So
Yeah, but the same in the other browser.
the same.
Yeah.
It's faster.
Yeah, this one has a lot of FPS.
Look at the milliseconds looks
Smooth scrolling and stuff, but on Firefox it's kind of stuck.
Yeah,
slow down.
Okay.
yeah, that is true.
Trying to disable JavaScript, there is a button.
The point of this demo is to show the difference between the browser, anyhow. It means like there's a few features of WebAssembly that must be supported in the post-MVP, and browser treated them differently, and there's many proposals. We'll see what Firefox is doing other than the two-tiered compilation we saw in the decode time. I want to show you also the gaming engines. This is Zen Garden. This is by Unreal Engine. I didn't download anything. I didn't install this game. It's fully interactive. I had many tabs in my browsers open with like something which is supposed to be intensive. My computer is not making a lot of sounds over. Like when I open 2 IDE editors at the same time. It's pretty relaxing. So there's no reason any game would be just a website. If we look for a second on Unity, they have a less relaxing one, but also a fully game. Let me reload it for a second because I want you to see how fast it loads the whole thing. Angry robots. I have a few more. By the time we made this lecture, Google dropped this Squoosh app, which is a comparison of images. It's quite different demo from the other ones. The other ones we saw was mostly in WebAssembly, or the main part was WebAssembly, and we saw how better it is to have things there. But if let me choose a random image. You can see I can choose my my compression here. Which one do I want? And choose another one here. And play with the quality. And compare between the two. And it shows me what's the... Can you see it? It's right here. But it shows me how much kilobyte I saved and what's the final size. But what's interesting here, mostly, is the source code. It's open. You can just go and clone and install and change and fork. And so I went and took a peek. And I found some code that should be a little bit familiar by now. You can see here they have a WebAssembly model, WebP, in this WebP encoder in this case. They init it with the URL and get the model, await for it, and then use the function they exported in code with the data from the image. Meaning all of their app, the client app, is HTML, JavaScript, CSS as we know and write, and they just have a few encoders in WebAssembly logic that they probably had from before in a language which they just compile to WebAssembly and can use now to compress on the client. Not sending to the server and get a compressed file, but the client can now compress because it uses the same server logic in the client side with not a lot of effort. I think it's pretty impressive. Okay, that's it for the demo. Sorry, let's quickly go back. Oh, I skipped this one. After Unity moved from ASM to WebAssembly, they had a nice blog, it's worth reading, about the benchmarks, like what different they saw in moving from one portable language to the other. So here we can see two things. Like first, it looked good. There's a big drop, other than Safari, which wasn't so good. It was better in WebAssembly in ASM. The red one is ASM and the blue one is WebAssembly. So it did better in ASM in comparison to WebAssembly, and even in WebAssembly is coming in last. Mozilla is in the win as always for now. We see if Chrome catch up. But for example, Chrome is a huge improvement when they move to WebAssembly. It's like, what is it, 4 or 5 times better. And this is a tweet I thought it's worth sharing. So let's take a look into the future. As we said, now it's since 2017. It's the MVP, and it's not the end game for WebAssembly. It's like the first version. All the browser decided they will backward support and have the minimum set of feature they can live with to start going. But we want more. We saw some application, but we didn't see any heavyweight application. There's big application, there's a Lightroom and there's AutoCAD, but it's hard getting like a big application to work because there's missing stuff. There's missing 64-bit support. They're missing SMID, same instruction, multiple data. It's for working with simultaneously, parallelly with big vectors. It's mostly for image manipulation. Threading support. Streaming compilation and two-tiered compilation is what we show on the download that I mentioned that Mozilla is already doing, but so far it's Mozilla only. And another one is caching. When I refreshed the Angry Robots, for example, I had to download the code again, and maybe not download the code, but I did have to decode and compile and optimize. This should be cached, and once I do it, refresh I should keep on going in a second. Or less. On the other end, if we talk about big application, we also need a solution for small application. Again, we as a developer, we need tools that will help us to solve our problems quickly, go home early. And NPM, for example, now kind of give us this. Like I can find a piece of code somebody else wrote, which is free to use, and have a big star ranking. And I said, okay, I import it, I use it, I'm done. I'm a genius. You saw what I have to go through to use a simple function of WebAssembly with all the memory usage. And one thing I didn't mention is I passed an integer and got an integer. You can do much more with direct parameters, passing and receiving. Integers and float. If you want to do something else, like strings or array of data or object, you have to use the memory. The browser support through the memory. You can get a reference to the memory and write there on WebAssembly and read it as a byte array in JavaScript or vice versa. So there's a shared buffer. But it's less elegant and not so easy to use. There's more stuff missing. Toolchain integration, we do import, export pretty easily. It's not the case. The calls between JavaScript and WebAssembly, other than Firefox, take like between half a second and a second to go back and forth. Its overhead is crazy. Mozilla, thankfully, shows they can do it even better than JavaScript calls to themselves. Like they reduce the time to nothing, but until the other browser will support it, it will still be hard to go for a lot of small changes, there and back and there and back. What else do we want to see? We want to see more languages compiled to JavaScript, where Java is not yet fully supported. C#, all of them. We want to take any code we have in any language and just put it in the browser. And we want to replace our frameworks. So we don't want them to, with framework work the hardest. We want them to use parts or in WebAssembly or big parts or all of it. But for this, we're missing other stuff. We need garbage collection integration. They have to decide who's responsible to prevent cycles and loops. Exception handling, I didn't open the debug panel for a reason. It's not in a good state. And tail code recursion are really important for that too. Sorry. Before that, I just want to say, maybe you know this, I didn't mention, but this is from the link art cartoon intro for WebAssembly. You probably recognize the style already. It's really recommended. You can see the measure in the side. It means what's the phase of the work. If it's in a proposal, if it's under work, if they didn't start working at it at all. And it's nice to notice most of it is at least in some kind of work. So we expect to see the behavior change in the close time. People are working on it as we speak. questions. For me, for Noam, for any part of the lecture. Yeah.
What's the state of WebAssembly on Node.js on the server side at the moment?
Node.js and server, I actually don't know. Not aware.
And does the JavaScript compile to WebAssembly? Probably not.
Sorry?
JavaScript, does it compile, or will it ever compile?
I can answer that. So JavaScript will never compile because it's not strict enough to be able to compile down to WebAssembly. But there is a project called assembly script, which takes TypeScript and compiles it down to WebAssembly. That will work. That already exists.
Also, there's a feature called binary ASTs, which will speed up those JavaScript parsing steps, just because JavaScript will be encoded in binary ASTs. So it is possible to have it, but if you want to do it in WebAssembly, you will have to compile your JavaScript engine to WebAssembly also. So you will be running JavaScript engine on your JavaScript engine to run your compiled code.
JavaScript inception.
Yes.
At the end, you had it already that the port right now is more for bigger or heavy applications, but the question I think that remains is because this context switching still costs a lot if you do it or use the WebAssembly for smaller things. Will it ever be necessary to use it for smaller applications, or will it just remain for the game engines or whatever? Or will it completely replace it, JavaScript, in a way? Because if you have a costful context switch between the WebAssembly and JavaScript, then it's a question: are you sticking just with JavaScript for websites, or will you really have it as fast and you don't need JavaScript at all anymore?
Well, it's regarding the cost. Mozilla solved it. The cost is it's the state of the current browser, which are not Firefox, but it's not. It shouldn't be costful. Like in Firefox, it's not costing any more than regular call. So this is not an issue. But I don't think it will mean it will replace JavaScript, because JavaScript has a reason to be alive of its own. It's more parts of JavaScript. For example, React Virtual DOM, the one we keep comparing to see event. There's no reason that wouldn't be in a different thread in WebAssembly if the call, as you say, is cheap, so we can go back and forth pretty fast. But it doesn't mean we have to replace all the framework, just the one that cost us in a lot of computation time.
What about debuggability, stack traces?
Horrible.
As expected.
Yeah.
Can you cause a seg fault?
Sorry?
A segmentation fault? Can you cause it?
I don't know. It's barely exists. It's there's a proposal and there's work, but this is one of the biggest limitation to work now with WebAssembly.
It's also sandboxed, or?
Sorry?
It's also sandboxed in a way, or regarding security issues, it opens, of course, a completely new box again.
Yeah, it's sandboxed. There's security. I don't know. I'm not aware of. I think it was part of the MVP or the security concerns. I'm not aware of any security proposal in work. Yes.
Just before I take that question, I'm sorry I have to leave. I have to catch the flight. So thank you everyone for having me.
Have a good flight, man. Yeah, maybe last question because the next lecture have to start.
Give us how strict is the WebAssembly environment? Can it access all the APIs, Node.js?
No, there's a lot of. I didn't go over everything, but that's a good question. There's other missing with the API of a DOM, accessing the DOM, and I think there's a bunch of stuff that you can do in JavaScript and can't do in WebAssembly. So you have to go back to WebAssembly and do use the API by JavaScript, and then go back to WebAssembly and hand him the change or answer, and it's costful if you didn't figure out how to reduce cost between modules. So this is also part of the you have to go through. Okay, I think you're good for the next talk. This is a list of resources we use. We're gonna probably publish the lecture on the meetup group. Thank you very much.